Welcome back. This is segment one of section 1.2. In this section, as I mentioned in the previous video, we are going to start looking at some geometric results. I'm certainly not going to prove them. I mean, maybe some minor proofs, but I don't really see the whole lot of point. You spent at least probably a year in middle school or high school studying geometry, and some of these results should be pretty obvious. But just they come up at this point because some of the stuff that we do, especially application-wise, requires you to kind of have some sort of spatial awareness of things, and some of these sort of that are, you know, hallmark benchmark sort of results are things that you should have in your utility kit, but maybe something that you've kind of forgotten about. So let me we're gonna define a few things. We're gonna have some results. But this is not nearly as long as section 1.1. However, it is very dense. But again, most of these results should be, you should already probably know them. Okay, so first, so we're now in section 1.2, page number 1. So let's talk about some other descriptions involving angles and some of the results of angles. So the first thing I want to talk about is what's called a vertical angle. Now, it's not a huge result, but a vertical angle, it's kind of a strangely worded term. Like when you think vertical angle, you're thinking, oh, like an angle from the vertical or something like that. But that's really not what it is. When you have two lines that intersect, like so, you will end up with pairs of angles, like this one and this one, that are have, well, as long as we're measuring these as positive between 0 and 360 degrees, right? With that whole measure, we could have, you know, round the horn 6 or 7 times. But the measure of these two angles is coterminal, right? Assuming that the rotation's the same way. Okay, well, blah 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 blah. But these are really geometry results. These two angles are congruent. So are these two angles. Now, they're not necessarily congruent this way, but they're congruent with their sort of opposite angle. Those pairs of angles are what are called vertical angle pairs, or they're called, this angle is vertical to that one, or this angle is vertical to that one. So, so here's kind of what a vertical angle is, and the statement: vertical angles are congruent, meaning they have exactly the same shape. When it comes to measure, it depends on which side's the initial side, which side's the terminal side, how many times you go around. I mean, all those sorts of other intricacies that are related to trigonometry, but for geometric purposes, they're the same. Okay, so that's sort of the first one. Here's something. I'm going to define what's parallel. So if two lines do not intersect, they are said to be parallel. Parallel is kind of a big topic in geometry because it's equivalent to a lot of other things. There's different aspects of geometry, non-Euclidean geometry, where you talk about what's called an elliptical geometry, which you could think of as kind of like how to do geometry on the surface of the sphere or some other sort of shape like that. You also have something called hyperbolic geometry, and they have different rules about parallelism. For example, if you define a line the way that we did, with any 2 points uniquely define a line, it turns out that you can't have any parallel lines on a sphere, on that surface. But in a flat space, like you're used to, Euclidean space, you have uniqueness of parallelism, which is to say that if you have a line and a point that's not on that line, there's one and only one line that's parallel, meaning it doesn't intersect. Now, there's some results that come out of that. If you're in flat space, then it turns out that those parallel lines are equidistant from each other and all sorts of other things. There's transitivity of parallel. So if one line is parallel to a second line and the second line is parallel to the third, then the first line is parallel to the third as well, or they're identical. So anyways, it's kind of a neat idea, but not really the subject of this course. So if we have, so a line that intersects a pair of parallel lines is called a transversal. And that's probably not a term that you're real familiar with, and we won't use it very much. It's just really for this example. Is this required? Well, a line that intersects a pair of parallel lines is called a transversal. It is possible in certain types of geometry to have lines that cross only one of the parallel lines. But we've really moved into a Euclidean space. So the assumption is that, you know, sort of the normal rules apply of geometry, and we can continue that way for the rest. But I always want people to be careful, because if you ever go back, you know, maybe later on in your academic career and start looking at these different types of geometries, these rules don't really work. It is possible to have a line that crosses one parallel line and not another. Or you could have one that crosses both, or whatever else, but you have to be in a different type of geometry. For Euclidean geometry, if you cross one, you cross the other. There's no other way around it. But to kind of give a picture of what I'm talking about, so imagine here are our two lines. Let's call them line M and line N. This is kind of a standard setup. You use lowercase letters for lines, names of lines, uppercase letters for points. And this sort of other line that comes through, maybe call it T for transversal, this is what we're talking about. We're talking about a transversal. So here's a geometry result. If you have this setup, and when we start talking about angles in here, these are what are called the interior angles of this arrangement. And this angle up here and this angle down here are the alternate, meaning they're on either side of the transversal, but they're alternate interior angles. They form an alternate interior angle pair, but this angle and this angle also form an alternate interior angle pair. And then, of course, you have vertical angles here, vertical angles here, vertical angles here, vertical angles here. So a geometry result is that the measure of alternate interior angles are congruent. Well, maybe I should remove, let me just remove this statement, the measure. Alternate interior angles are congruent. That means they have the same shape. When we get into measure, it's like you got to be careful which one's the start and the end. So to use some of that geometry looking symbolism where you use certain numbers of lines to represent congruence. So this is congruent with this. And this angle here is congruent with this one. So this is this is kind of that geometry symbolism saying that these two angles are congruent. And if you start with the right initial side and terminal side, they have the same value, the same measure. Now, from combining these two results of vertical angles and alternate interior angles, you can continue and say, well, if this angle is vertical to that one, then these must be congruent as well. Similarly down here on the bottom. And then also if we compare these two vertical angles, they are also congruent by the previous statement. And so we end up with something that looks like this, where we have this angle is congruent to that angle, congruent to that one, congruent to that one. And similarly, this angle is congruent to that one, congruent to that one, congruent to that one. They're all congruent to each other. There are a couple of problems in the text where you have a couple of lines sort of, coming together and whatnot, and you're given some minimal amount of information about maybe one line or one angle, and you're supposed to find some others. So I'm just reminding you of this geometry result because it does come up. Okay, so we have a transversal. What about a triangle? So we're going to create a very formal definition for a triangle. So a triangle is an object formed by three distinct lines. Now remember, let me finish this sentence, that intersect at three distinct points. So this is sort of a statement about, remember, distinct means they have to be different. So sometimes when you're creating these sort of definitions, you have to be real careful about like some special cases. We are really talking about different lines and different points. So neither one of these two lines can be parallel, otherwise they don't intersect each other and you don't end up with the three distinct points. But this is really exactly what you think it is. And I'll maybe like draw a little picture over here where we're constructing these. Here's your three lines. And notice if they're not the same line, or if none of them are parallel and aren't all coincident at a single point, like you could have all three of them radiating from a single point, you're going to end up with this shape kind of in the middle that's a triangle, okay? And that's going to be kind of critical because we're creating all these angles out of rays and things like that. So anyways, this divides, this arrangement divides the plane into, well, there's 7 different regions. Six are unbounded, meaning they have sort of infinite area and whatever else. And there's 1 bounded region. The bounded region is the so-called inside of the triangle. So I'm going to get a little hand wavy here because it's kind of hard to define this stuff in a way that's not super meticulous, and you probably won't really appreciate it anyways. But essentially, the triangle can be thought of in multiple different ways. It can be thought of as just these line segments, right? But you almost always have to think of it as the area that's inside here as well, the area or the space that's contained inside these 3 line segments. Now you're going to end up creating angles at each vertex, and in this case there really are 3 vertices, inside the triangle, and there's some results that come out of that, which you probably already know. So let me go ahead and continue with this idea. So an angle is said to be an interior angle if any of its interior lies on the inside, it lies in the inside of the triangle. This all just sounds like I'm kind of defining things with the same words. So what's the inside of the triangle? The inside of the triangle is this area that's contained inside these line segments. When we're talking about an interior angle, we're talking about, so here's a ray, here's a ray. The interior of the angle is the space that lies between the two rays. And so since some of that space is inside the triangle, this is called a interior angle, whereas there are exteriors. That's another term that we won't even get into, but it turns out that this kind of weird thing is actually an exterior angle. And this whole thing, if you remember from our, notice exterior angles are supplementary to interior angles, and the sort of excess is what's called the explementary angle. But like I said, those terms aren't really super critical to us. And I'm just going to say there are always three such angles. So basically, a triangle has three vertices. Not a shocking result. So note, and I'll just kind of put a note here, and I think my video is getting a little long, but I want to finish with this idea. So note, the measure of any interior angle let's call it theta, falls in the range between 0 degrees and 180 degrees. That's for a real triangle. Now we could have a triangle that's like smashed in some way so that it's sort of a weird thing, but the triangles always have non-zero angles in their interior. And the most that they could ever be is just shy of 180 degrees, because there's some results that we already know about, which is that well, I'll get to that in the next segment. Like I said, we're getting a little bit long, and I'd like to keep your interest, so I'll see you in the